Hi everybody, I am Bharathi from Sri Saratha College for Women, Autonomous, Salem 16. I am going to explain about clusters and weights rule. A metal cluster may be defined as a group of three or more metal atoms in which there are direct bond between metal atoms. It may be have molecular complexes with metal-metal bonds that form triangular or larger closed structures. A large number of metal carbonyl clusters exist for the elements of group 6 to 10. The transition metals from 6 to 10, mostly heavier transition elements, form clusters. Before going to see about the clusters, we should know about 18 electron row. Metals up to 5 obeys the 18 electron rule. After that, it obeys the weights rule. A stable transition metal complex is formed when the sum of d electrons, donated electrons by the ligands, and charge on the complex is equal to 18, is called 18 electron rule. In this, Ns, Np, and Nd orbitals are involved. Totally, 9 orbitals are involved in the 18 electron rule. Transition metals forms two main classes of metal-metal clusters: halide or oxide clusters and carbonyl clusters. Halide or oxide clusters are generally formed by early transition metals such as niobium, tantalum, molybdenum, tungsten, and rhenium. On the other hand, the carbonyl clusters are many. The carbonyl group can occupy either the terminal or bridged position. It contributes 2 electrons in each case. Cluster formation is the result of electron deficiency in MCON fragments. The reason is that the fragments from which metal clusters are made are electron deficient, sometimes substantially so. The triangular clusters OS3 CO 12 times can be regarded as a stable trimer of the unsaturated fragment OS CO 4 times. Why we called it as unsaturated means osmium group number is 8, so it contains 8 electrons. Each carbonyl donates 2 electrons, 2 into 4, 8. So 16 electrons are present in OSCO 4 times. So it is unsaturated. While in the case of RHCO thrice, it contains only 15 electrons. So it is even more electron deficient and form a tetrameric RH4 CO12 types with the tetrahedron of metal bonds. Since electrons are available once or shared out over the clusters as a whole, so that the system is really fully delocalized. Metal-metal bond formation is most likely to occur when the metal atoms are in their lower oxidation states. Therefore, the most extensive class belong to carbonyl clusters, in which the formal oxidation state of the metal is 0 or negative. The tendency to form the metal-metal bond is usually greater for heavier metals. So, it is subdivided into two: low nuclearity carbonyl clusters and high nuclearity carbonyl clusters. Nuclearity means metal atoms. These clusters contain small number of metal atoms, 2, 3, or 4 in their structure. High nuclearity carbonyl clusters have 5 or more than 5 metal atoms directly bonded to each other. Now we will see about calculating the metal-metal bond. First, we have to calculate the total valence electrons in the complex. That is, the number of valence electrons on the metal plus number of electrons from each ligand and charge. We have to say it as A. Subtract this number from n into 18, where n is the number of metals in the complex. That is, n into 18 minus A, say it is B. B is divided by 2, gives total number of metal-metal bonds in the complex. If you want individual metal, we have to divide by n. It gives the number of electrons per metal. If the number of electron is 18, it is indicated that there is no metal-metal bond. If it is 17 electron, it indicates that there is one metal-metal bond. If it is 16 electrons, it is indicated that there are two metal-metal bonds. Now let us see one example. Fe3CO 12 times. Iron, 3 iron atoms are there. So 3 into 8, that is 24. 12 carbonyl donates 24 electrons. Total valence electron is 48. This is A. In this case, 3 iron atom is there. So n is equal to 3. 18 into 3, that is 54. Minus A, that is 48. That is gives 6. 6 divided by 2, it gives 3. This is the total number of metal-metal bonds. If you want to know the individual metal bond, we have to divide 48 divided by 3, that is equal to 16. So 18 minus 16, that gives 2. So each metal has 2 bonds. This is the basic geometry of Fe3CO 12 times, that is triangular. The next example is CO4CO 12 times. Gopal, 9 electrons in the outermost shell. So 4 into 9 plus 12 into 2, totally 60 electrons are present in the valence shell. Now, 4 into 18 gives 72 minus 60, that is equal to 12. 12 divided by 2, that is 6 total metal-metal bonds are present. Here, 60 divided by 4, because 4 is the metal atom. So, 60 divided by 4 gives 15. 18 minus 15 gives 3. So, each carbonyl has 3 bonds. The basic geometry is tetrahedral. Another example is mu CO twice, eta 5 Cp, RH thrice CO. The total valence electron, if you calculate in negative way, there is mu CO donate 2 electrons. So 2 into 2, 4 electrons. Eta 5 means negative method, it has 6 electrons. And RH has minus charge, so 8 electrons. It is multiplied by 3 plus the carbonyl, terminal carbonyl has 2 electrons. So we got to add 2 electrons, totally 48. In neutral method, that is mu CO2, mu CO are there. So 4 plus eta 5. So 5 plus RH has 9 electron in the outermost shell. So 9 into 3 plus 2, that is 48. Here, 3 rhodium are there. So 3 into 18 minus 48, that is gives 6 by 2, that is 3 metal-metal bonds are present. Here, 48 divided by 3, that gives only 2, that is 16. 18 minus 16, that gives 2. So each rhodium has 2 metal-metal bonds. These are the other examples. Now, we will see about the trinuclear cluster. Most trinuclear clusters are triangular, with each metal atoms bonded to both the others. The triangular clusters OS3CO12 times can be regarded as the stable trimer of the unsaturated 16 electron fragment OSCO4 times can be considered as achieving 18 electrons by forming 2 metal-metal bonds, one with each of the other 2 metal atoms. On this counting convention, OS3CO12 times, that is 3 metal atoms, so 3 into 8 electron plus 12 into 2, 48 electron in the cluster. This is approximate number of electrons for a triangular cluster. We have 3 into 9 orbitals, that is 27 orbitals, has the capacity of 54 electrons. Here, only 48 electrons are present. So 54 minus 48, that is equal to 6 electron. That is divided by 2 gives 3 metal-metal bonds. The clusters are triangular. Fe3 skeleton of Fe3CO12 times has 48 valence electrons, and Fe3 unit contains 3 Fe single bonds. Most trinuclear clusters are triangular, with each metal atoms bonded to both the others. In the case of Fe3CO12 times, it has 2 bridging carbonyls and 10 terminal carbonyls. But in the case of ruthenium and osmium, which belongs to the same group, there is no bridging carbonyls. All are terminal carbonyls. Now let us see about tetranuclear clusters. 4 atoms clusters occurs in 3 fundamentally different geometries. Most of the tetranuclear clusters are regular tetrahedra, but significant group takes the butterfly-like structure. The 15 electron fragment of IrCO3 forms IrCO3 4 times, which has an iridium 4 core in the shape of the regular tetrahedron. In this complex, all the carbonyl groups are terminal. The isoelectronic complex, that is same number of electrons in CO4CO12 times and RH4CO12 times, have nearly tetrahedral arrays of metal atoms, but 3 carbonyl bridges are present in the triangular faces in each of these clusters. The tetranuclear group, that is 9 clusters, group 9 clusters, belongs to cobalt, rhodium, iridium, forms M4CO12 have 60 electrons. As expected, a tetrahedral cluster framework with 6 M bond M formation is adopted. In other tetranuclear clusters, carbonyl act as a terminal, bridging, and triply bridging ligands. In the special case of the butterfly geometry, all the atoms are in the plane with the dihedral angle of 180 degree. Here, let us see how to calculate. Metal valence electron, in the case of iridium, 4 iridium atoms are there. So 9 into 4, that is just 36. Each ligands donate 2 electrons. Here 12 ligands are present. 12 into 2, 24 electrons. Here there is no charge at all. So the total electron is 60. Here 4 iridium atom is present. So 4 into 18 gives 72. 72 minus 60, that is 12. 12 divided by 2, that gives 6 metal-metal bonds are present in total. Metal-metal bonds are present in IR4CO 12 times. In this case, each iridium atom has 3 bonds. All the carbonyls are terminals. There is no bridging in iridium complex. The cobalt and rhodium belongs to the iridium complex group, but the cobalt and rhodium has 3 bridging and 9 terminal carbonyls are present. Next, we will see about high nuclearity carbonyl clusters. The high nuclearity carbonyl clusters are large, often structurally complex, and most of them contains heavier, that is second and third transition metals. These clusters contains 5 or more than 5 metal atoms directly bonded to one another. These clusters often involves extensive metal-metal bonding and are stabilized by ligands such as carbonyl groups, hydrides, and bar or other donor ligands. Now, pentanuclear clusters are normally triangular in shape. Basic one is triangular. It normally forms trigonal bipyramidal in their geometry. Here, this is triangular and then bipyramidal. These two are bipyramid. In this case, here there is no bridging carbonyls. All are terminals. Carbonyls. Hexanuclear clusters. Hexanuclear clusters are most commonly octahedral, but 4 other geometries are known. A capped square pyramid, a bicapped tetrahedron, a trigonal prism, and a triangular planar network. Heteroatoms in clusters such as Fe4CO13C or Fe5CO15C are located interstitially and do not occupy a vertex. All the heteroatoms valence electrons are contributed to the skeletal electron count. Each rhodium acquires 4 electrons from 2 terminal carbonyls, has a share of 4 electrons in 4 RH-RH bond. This is the octahedral structure of RH6CO16. In this, 4 triply bridged carbonyls are present. Here see, This is triply bridged carbonyls. Remaining 12 are terminals carbonyls. Now, let us see about the weights rule. A semi-empirical correlation of electron count and the structure of large organometallic clusters was introduced by K.BHARATHI and refined by Mingus and Luhar. This counting scheme is referred to as the polyhedral skeletal electron pair theory, PSEPT. This polyhedral electron pair theory provides electron counting rules useful for predicting the structure of clusters. Weights rules apply to the class of polyhedra called deltahedra. The geometry is consisting of polyhedral, all of whose faces are equilateral triangular, or those polyhedral with one or two vertices are missing. Let us see the rule. The first rule is add all the valence electrons of all the metal atoms in the carbonyl clusters. Add 2 electrons for each carbonyl, whether it occupy in terminal or bridged position, to the total valence electrons obtained in step 1. The step 3 is add 1 electron each for each negative charge, if any, to the total electron obtained in step 1 and step 2. The fourth rule is add total number of electrons obtained up to step 3, the number of valence electrons of each interstitial or encapsulated atoms, if any, that is add 1, 4, 5, and 5 electrons respectively for encapsulated hydrogen, carbon, nitrogen, and phosphorus atoms. The fifth rule is keep in mind that it is important assumption that in addition to electrons necessary for skeletal bonding, each metal atom utilizes 12 electrons for non-skeletal bonding with metal carbonyl groups. In this, we should know 12 electrons are not involved in cluster formation. Only remaining electrons are involved in the cluster formation. In the three CO groups of the OSCO3 fragment supply 6 electrons, and these electrons occupy 3 of the metal's 9 orbitals. 6 of the 8 metal electrons occupy d pi orbitals and backbone to the carbonyl group. 2 of the metal electrons are left to fill the 3 cluster bonding orbitals are shown to the right of the dotted lines, Transition metal has 9 orbitals. Out of that, 6 are not used for cluster formation. The number of vertices in the deltahedron is 1, less than the number of bonding pairs in the framework. This approach is sometimes called the polyhedral skeletal electron pair theory or Weights rule. Here, the number of skeletal electron pair is 6 means it adopts the structure of trigonal bipyramid. If it is 7 means it form octahedron. If it is 8 means pentagonal bipyramidal. Likewise, it goes on. The 18th electron rule is suitable for identifying the correct number of electrons in the clusters with fewer than 6 metal atoms. The Wade-Mingus-Luhar rule identifies the correlation between the valence electron count and the structures of large organometallic compounds. Let us see the types of structures, that is closo. Closo means caged or closed, completely closed polyhedral structure when n metal atoms. Nido means nest-like structure. It has n plus 1 cornered polyhedron. Arachno structure. It is a spider web-like structure. Even more open clusters in which the metal atom occupy at the corners of an polyhedron, that is 2 plus n rule is formed. Hypo has net-like structure, have the most open clusters in which metal atoms occupy the corners of an n plus 3 cornered polyhedron. Clado is called a branched structure, that is n plus 4 cornered polyhedron. Now, in the metal cluster follows transition exclusively. Transition metal clusters form 14n plus 2, 14n plus 4, and 14n plus 6, and 14n plus 8 rules. Polyhedral electron counting n plus 1 gives closo, n plus 2 gives nido, n plus 3 gives arachino, n plus 4 gives hypo. So here n is the metal atom, number of metal atom. Let us see one example. Fe5C CO15. In this, Fe has 8 electrons in the outermost shell. So 5 into 8 plus 15 into 2 carbonyls plus 1 carbon has donate 4 electrons, totally 74 valence electrons. In this 5 Fe, that is in the 5 Fe, 12 electrons, each Fe, 12 electrons are not involved in cluster formation. So 5 into 12, that is 60 electrons are in non-cluster formation. So you have to subtract from 74 minus 60. It has only 14 electrons for cluster formation. Here, 14 divided by 2 gives 7 pairs. In this, 5 Fe atom is there. So 5 plus 2, that is equal to 7 pairs. It forms nido structure. In this is the skeletal electron pair. This 7 skeletal electron pair less than 1 is the geometry. So it form octahedral geometry and one vertex is missing. These are the other examples. Let us see only one example, that is RH6CO16. Rhodium belongs to 9th group. So 9 into 6 plus 12 into 2 gives 86 electrons. In this, n is equal to 6. So here, 86 minus each rhodium non-bonding electron is 12. So 12 into 6. So 86 minus 12 into 6 gives 7 pairs. So 6 plus 1 gives 7 pairs. So it will come to closo structure. And this is the skeletal electron pair. Less than 1 is the geometry. So it occupies the octahedral structure. Now let us see MCQ. The first question is the total valence electron count and the structure adopted by cluster Fe5CO15C respectively are. Here we have to follow that is 5 Fe donate 8 5 into 8, that is 40 electrons. 15 into 2, 30 electrons, and carbon donate 4 electrons. Totally 74 electrons are present. Then you have to follow this rule, that is spec is equal to polyhedral electron count is equal to total electron count minus 12 electrons per metal atom is not involved in cluster formation. So total electron count is 74 minus 12 into 5. 12 into 5 is 60. 74 minus 60, that gives 14 electron, divided by 2 gives 7 electron pair. Here, 5 metal atoms are present. 7 minus 5, that is 2. So, it come under n plus 2 cluster formation. So, it is in nido structure. Nido means it has nest-like structure, and also it occupies the octahedral geometry. One vertex is missing. Let us see the second question. Which metals of the following have greater tendency to form metal clusters? Mostly heavier transition metals forms metal clusters more. In this, osmium, iridium, and rhodium form this metal clusters more readily. The third question is the correct statement regarding terminal bar bridging carbonyl groups in solid CO4 CO12 times and IR4 CO12 times. In the IR4 CO12 times, there is no bridging carbonyl group. So, the number of bridging carbonyl groups in IR4 CO12 time is 0. The fourth question is, according to Wade's rule, cluster OS3CO12 time is type of. Here also we have to multiply similar like heavier clusters. That is OS has 3. So 3 into 8 electrons in the outermost shell. So 24. Each carbonyl donate 2 electrons. So 12 into 2, 24 to. So here totally 48 electrons are present. Here we should follow PEC. That is PEC is equal to total valence electron minus 12 n per metal atom. So total valence electron is 48 minus 12 into 3. That is 36. 48 minus 36 gives 12 electrons. 12 divided by 2, 6 pairs. Here totally 3 metal atoms are there. So 3 plus 3 gives arachino structure. The fifth question is, how many metal-metal bonds are present in CP, MO, CO 3 times twice? Generally, CP donates 5 electrons in neutral method. Molybdenum donates 6 electrons. 3 carbonyl donates 6 electrons. Totally 17 electrons. Here, it is in twice formation. So 17 into 2, that gives 34 electrons. Here, 2 molybdenum is present. So 18 into 2, 36. 36 minus 34, that gives 2 electrons. 2 by 2, it gives 1 metal-metal bond is present in between molybdenum and molybdenum. The last one is the cluster having arachino type structure is, in the case of Ru5C CO16, ruthenium, it come under iron family, that is iron, osmium, ruthenium. So here, 8 into 5. 8 into 5 means 40. So carbon donates 4 electrons and 12 carbonyl groups, 16 carbonyl groups donate 32 electrons, total is 76. In this, 5 ruthenium, 5 into 12, 60 electrons are not involved in cluster formation. So 76 minus 60, that is 16, divided by 2 gives 8 pairs. So here, only 5 metal atom is present. So N is equal to 5 plus 3, that is equal to 8. So N plus 3 rule is formed. It is coming under Arachino structure. Thank you all for watching. Bye.